Hello students, this session is on linear combination of vectors. The definition is like this: let V be a vector space over the field F and alpha 1, alpha 2, alpha 3 up to alpha n belongs to V be any n vectors. We are taking n number of alphas from the set vector space. Any vector in the vector space takes the form C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 up to Cn alpha n, where C1, C2, C3 up to Cn belongs to the field F, is called linear combination of vectors alpha 1, alpha 2, alpha 3 up to alpha n over the field F. That means we are taking n number of alphas from the vector space together with the scalars C1 to Cn. We are writing in linear combination. Linear combination means we are writing in addition of scalar multiplication of C1 and alpha 1. Sum of scalar multiplications of scalar with the vector. That means C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 up to n vectors. Like this. This form is called linear combination of vectors. Another definition is on linear span of a set. Linear span of a set. Let V be a vector space over the field F. W be any non-empty subset of V. Linear span of W is denoted by L of W and it is defined by the set of all linear combination of finite elements of W. That means L of W is a set. L of W is a set. It is called linear span. What it contains? Each element of L of W, each element of the set L of W is in the form linear combination of finite elements of W. Finite elements means n number of elements taken from the set subset W. Taken from the subset W. L of W means taking n number of elements from W, we are writing a linear combination of those vectors from W. That's what it is said, that set of all linear combination of finite elements of W. That means each element of the L of W is of the form linear combination. Here we have one note. L of W equals to V. V is a vector space. L of W is the linear span of a set W. So L of W is equal to V means what? Every element of V is a linear combination of finite elements of W. As said in the definition, L of W itself is the set of all linear combination of finite elements of W. So that L of W equals to V means in V every element is of the form linear combination of finite elements of W. Each element of V is nothing but, for example, if alpha belongs to V means alpha exists as not a vector. It's a vector can be expressed in the form of linear combination. Any vector can be expressed in the form of linear combination of finite elements. Now let us see some theorems on linear combination of vectors. First theorem is on to prove that set of all linear combinations of any vector in a vector space is a subspace of V. Is a subspace of V. Or it is also given to be L of W is a subspace of V of F. V of F means vector space over the field F. L of W means what? It is a linear span of a set. Linear span of a set means what? It is the set of all linear combination of any vector. Set of all linear combination of any vector. So instead of L of W, it has to be given as set of all linear combination of any vector. Proof is like this. Let L of W be the set of all linear combination of finite elements of W, as we know from the definition. We have to show that it is the subspace of V. L of W is a subspace of V. What is a subspace? Subspace of V means it has to satisfy both the conditions, vector addition and scalar multiplication. Before that, it has to satisfy, it is non-empty subset of V. So it is non-empty means what? It has at least 0 vector. But any vector, if it has to belongs to L of W, it should take the form linear form, because L of W is the set of all linear combination of finite elements of W. Since W is a subset of V, V means vector space. We have finite elements in W, so that those finite elements are alpha 1, alpha 2, alpha n. So any vector, any 0 vector can be represented in the linear combination of alpha 1 to alpha n elements of W. As such, 0 into alpha 1 plus 0 into alpha 2 up to 0 into alpha n. This leads to a 0 vector. So this 0 vector belongs to L of W means L of W is non-empty. Clearly, L of W is subset of V, because W is a subset of V. L of W is the linear set of all linear combination of finite elements of V means finite elements of W means it is the subset of V. L of W is subset of V. Clearly, now L of W is a non-empty subset of V. So to prove it is a subspace of V, L of W is subspace of V, let us consider two vectors from L of W. Two vectors from L of W, alpha, beta. So each vector, each alpha vector and beta vector, takes the form linear combination of n elements of n vectors of W. That means write alpha as the linear combination of n vectors. What are those n vectors? Alpha 1, alpha 2, alpha 3, alpha n. So linear combination means it is the combination of scalar and vector. So take a1, a2, a3, an as scalars. So a1 alpha 1, it's the scalar multiplication of vector. So a1 alpha 1 plus a2 alpha 2 plus a3 alpha 3 up to an alpha n, it belongs to L of W. We are taking alpha in L of W means alpha is in the form linear combination of n elements of W. So similarly, beta is the linear combination of b1 beta 1 plus b2 beta 2 plus b3 beta 3 up to bm beta m belongs to L of W, linear span. So we have written linear combinations means we have to define where it has come. That means a1, a2, an, these are the scalars, b1, b2 up to bm, these are the scalars. So belongs to F, the field F. Likewise, alpha 1, alpha 2, alpha 3, alpha n, beta 1, beta 2, beta 3, beta m. These are the vectors. So these vectors, finite vectors, belongs to W.